Ward here. I want to talk to you today about thermodynamics. And if you're thinking, man, I'm not sure that's a topic we're covering today, we're talking about this because it underpins how we think about energy and the changes that energy goes through in our system. So I want to start off with just a quick review, reminding you that there are three types of energy. The first is what we call kinetic energy, and that's energy associated with motion. And I'm using the capital E here to denote energy, and I'll try and do so consistently throughout our class. So kinetic energy is the energy that an object in motion has with it. And so an easy example to think about is fluid flow. That could be water in a river, that could be air in the atmosphere, but that fluid flow has energy. And we know that because we can extract it with things like turbines and turn it into another form like electrical energy. And in general, we can think of kinetic energy as 1/2 times mv squared, where v here is velocity, m is the mass that's actually in motion, and then that Ke would be the kinetic energy in units of something like kilojoules in this case. Second major type of energy is potential energy, or PE, and this is energy related to position. The classical example of this is someone at the top of a slide. Right? You're not necessarily moving, so you could be there and be still, but you have the potential to exert energy. Right? You could turn your potential energy, your position, into kinetic energy by letting gravity pull you down the slide. So our definition for potential energy is mgz, where z is that elevation difference. Right? It's the positional energy that you have, or the positional distance. G is gravitational acceleration, so how fast gravity could pull you down from that position, or accelerate you downward from that position. M still mass, and again potential energy in units of kilojoules. The third type of energy we want to remember is that there is internal energy. Sometimes folks call this chemical energy. This is actually the potential energy and kinetic energy that's associated with atoms and molecules. And so a nice example of this is if you think about like a Cliff Bar, right? How is it that this little chunk of food gives your body energy, right? It contains chemical bonds that your body can break down during digestion. So internal energy is, you could think of it as basically energy bound up in chemical bonds and the structure of matter. So the total amount of energy that something has is a combination of its internal energy, its kinetic energy, and its potential energy. And just to remind you here, that's where those three terms come from. Now, a few more concepts that we're going to have to keep track of as we talk about thermodynamics and energy. One of those is the idea of heat. So heat is what we think of as the movement of thermal energy, and it's typically going to move from areas of high, to low concentration, or from hot to cold. Right? So heat flows from hot to cold. It can be transported, just like our mass could be transported by advection and dispersion. In terms of heat, we would call those processes convection and conduction. Right? And so you can remember that because a convection oven is the one that has the fan inside of it. It's convecting heat. It's moving it around. So convection is with motion. Conduction is more equivalent to our dispersion. It's moving, diffusing along a material. In SI units, we're going to think about calories as a description of heat. And 1 calorie is the amount of energy it takes to heat 1 gram of water by 1 degree Celsius. And if you're in the BG system, you'll think about heat in BTUs, which are British thermal units, and that's the amount of energy it takes to heat 1 pound of something by 1 degree Fahrenheit. So 1 BTU is heating 1 pound of water by 1 degree Fahrenheit. The other process or concept we're going to have to keep in mind with energy is the exertion of energy to do work. right? To cause something else to have energy. So to give energy from one system to another, or have energy done to our system. If we take a ball and move it to the top of the slide, we're doing work. We're exerting a force over a distance, and by doing so, we're putting energy into that ball. That's in contrast to power, which is the rate that work gets done. So, if we want a really tangible example, envision that our class is held on the 5th floor of a building. Right? In order to walk up the stairs to that room, we've all done the same amount of work, right? Because we've all, if we weigh the same, right? If we all have to carry the same object up that flight of stairs, what we'll see is that we're all exerting the same force over a distance. We might not all use the same power. I might meander very slowly up the stairs, whereas one of you might choose to jog up the stairs and get a workout. The power that we're exerting, the rate that we're doing work, could be different. So to differentiate these, we'll typically use a W for work and a W with a dot over it for power. And just a reminder that dot over a variable is our notation for a rate of. So power is the rate of work. One specific kind of energy that I know we'll deal with this semester is temperature. And in doing so, we need to describe it. Just like we use density to describe material properties that might come in handy, when we're thinking about thermal energy, we use a term called specific heat. And specific heat is how much energy it takes to raise 1 gram of a substance by 1 degree Celsius. We use a lowercase c with a p subscript for that. And so if we thought about a frying pan, a beautifully illustrated frying pan here, it generally has 2 pieces, right? So one element is metal. Now metal has a low specific heat. Right? That means it doesn't take very much energy to warm that pan by 1 degree Celsius. And that's good for us as cooks, right? It means it heats up, it's easy to heat it up, it's efficient, it's not wasteful. On the other hand, the wooden or the rubber handle is probably made of something that has a high specific heat. So you can put a lot of energy in, but it doesn't warm up very much. And we can use this concept of specific heat to ask how much energy do I have, just like we can use density to ask how much mass do I have. So specific heat in U, the internal energy associated with heat, we can calculate as mass, m, times specific heat, times temperature. So we can actually take a temperature and convert it into an amount of energy, or if we know an amount of energy, we can ask what would the temperature of this object be. To help draw some parallels to the way we've been thinking about the world, which is broadly through mass transport and the conservation of mass, there's a very clear parallel here between a mass balance and a thermal energy balance or a heat balance. So in a mass balance, we think about mass as the extensive property, the measurable thing, and the intensive property as concentration. Right? So a jar or a tank full of something has a mass, but we can also describe the mass per volume in it. So one is about the object in its shape. The intensive or intrinsic property of it is independent of amount. Similarly with energy, the way we measure that is temperature. And so just like we had concentration was mass per unit volume, we can think of temperature as thermal energy per specific heat times mass. And just to be clear here, that's a capital U. Again, that's internal energy, and here we're specifically thinking about thermal energy or heat energy in our system. Finally, we can bring it all together and we can think about an energy balance in the same way that we've constructed mass balances. So if we start from this idea of accumulation as inputs minus outputs, we can work through these key terms. So let me write this out and then we'll go look at it term by term here. So accumulation, we're thinking about the time rate of change of energy in the control volume. So how how is the energy inside of our control volume changing through time? Increasing, decreasing, remaining at steady state. That first term, the Q with the dot over it, thermodynamics will use this Q to describe thermal energy or heat flux or heat flows. So this is the net rate that thermal energy is being transferred in. And importantly here, you can see I'm highlighting in red, the assumption is that the system is being warmed. So as a consequence, there's an implied positive sign on that term. It's not minus Q dot, it's the Q with the dot over it. We can also have work being done by the system. And there, again, is an assumption there that the system is doing work. So it is giving its energy away or transferring it to something else. If work is being done on the system, then the net rate would be a positive. Right? So you've got to really watch these conventions. We're assuming that thermal energy is coming in as a default and that our system is doing work by default. Finally, these last two terms there's this lowercase e times a mass rate. And that lowercase e is the energy per unit mass coming into the system. And of course, that m with the dot over it is the mass rate. And so just like we would have had in a mass balance, we had something like a Q times C, like a flow in times concentration in. These terms are very parallel here. Energy per unit mass in times mass rate in, energy per unit mass out times mass rate out. And so that's the actual flows of energy associated with materials coming in and out of the control volume. So that could be something like warm air flows into the control volume. So we want to keep track of that actual advection of air and advection of energy into the control volume. All right, folks, so I hope what you take away from this is just a bit of a reminder on some of the key terms in an energy balance, how they relate to one another, and importantly, you can see the parallels between energy balances and mass balances. Everything that we've been able to do with a mass balance, we can repeat that same kind of process for an energy balance, and it adds one more tool to our toolkit. Thanks for sticking with me, and I'll see you all in class.